Suppose at time t naught equals 0, an object has an initial position of r vector equals x naught for the x component plus y naught for the y component, and an initial velocity of v vector at 0 equals v naught cosine of theta for the x component and v naught sine theta for the y component. Show that its trajectory is given by r vector as a function of time is equal to x naught plus v naught cosine theta times t for the x component, and for the y component, y naught plus v naught sine theta t minus 1/2 gt squared. Note, in 2 dimensions, the force of an object in free fall in a uniform gravitational field is given by F vector equals minus mgj hat, where y is the vertical axis, m is the mass of the object, and g is the free fall acceleration due to gravity. So to begin, let's just rewrite what we were given. We are given the initial position of the object is equal to x naught I hat plus y naught j hat. Notice, this corresponds to x at t equals 0 being equal to x naught, and y at t equals 0 being equal to y naught. The initial velocity of the object at time t equals 0 is given as having components v naught cosine of theta naught in the x direction and v naught sine theta naught in the y direction. This means that the x component of velocity at time t equals 0 is equal to v naught cosine theta naught, and the y component of velocity at time t equals 0 is equal to v naught sine of theta naught. We have to show that the position as a function of time given these initial conditions is equal to the position vector being x naught plus v naught cosine theta naught t for the x component and y naught plus v naught sine theta naught t minus 1/2 gt squared for the y component. So what we are given is Newton's second law of motion. Newton's second law of motion says that when you add up all of the forces on an object, it's equal to the product of that object's mass and its acceleration. Put another way is acceleration is directly proportional to the net force acting on an object and inversely proportional to the mass of the object. What this means is that an object will accelerate in the direction of the net force acting on it. Newton's second law of motion is often called an equation of motion. And the reason why is this equation of motion allows us to predict the future motion of an object if we're given a couple of initial values like we have here. We have the initial value of the object's position and its velocity. How this helps us is we know what the acceleration of an object is defined as. It's defined as the time derivative of velocity. So what this means is we could What this means is if we know an object's acceleration, we could integrate in order to determine an expression for its velocity. So this becomes the integral of the velocity differential from some initial velocity is equal to the integral from some initial time to some final time of the object's acceleration with respect to time. So the question is, what is the object's acceleration? Well, we get the object's acceleration from Newton's second law, which again, Newton's second law says an object accelerates in the direction of the net force that acts on it. So to determine the net force acting on an object, well, we know that this object is in free fall. Free fall is the state in which the only force acting on an object is the force of gravity. So here, if I illustrate this xy coordinate system, the free fall acceleration of gravity is just given as minus g j hat, where g is defined as the magnitude of the free fall acceleration due to gravity. Now that we know that the acceleration is given as minus the product of the object's mass and the free fall acceleration due to gravity divided by the object's mass. This means that the object's acceleration under the influence of gravity alone is just equal to minus g vector. With that said, we have the integral from some initial velocity to some final velocity of our velocity differential is equal to minus g, the free fall acceleration due to gravity, dt integrated from some initial time to some final time. The integral of dv becomes just v, the velocity vector, evaluated from some initial velocity to some final velocity. And I really should put my velocity vectors here because velocity is a vector and we should indicate that. Now on the right side, the free fall acceleration due to gravity is a constant. So this comes outside of the integral. And we have the integral from t naught to t dt. Well, the left side of this ends up being our velocity function. So the velocity is a function of time minus the initial velocity as a function of time is equal to minus g vector times t evaluated from t naught to t. Isolating our velocity as a function of time, we have on the left side the velocity as a function of time expression, and on the right side our initial velocity at time t naught minus g vector t minus t naught. Well, for simplicity, let's recognize that t naught is equal to our initial time. T naught is equal to 0. So this means that our velocity function is equal to our velocity at time t equals 0 minus gt, where this expression for t naught goes to 0. Well, remember, our initial velocity was given with an x component of v naught cosine theta naught and a y component of v naught sine theta naught. What that means is that our object was given an initial velocity that has an x component and a y component projected at some initial angle above the horizontal. And we know that object is going to follow a parabolic trajectory, at least from our experience. This problem will hopefully confirm that when we solve it. Well, we know our expression for the initial velocity. Let's go ahead and plug in what we know into our velocity function. Velocity as a function of time is equal to our initial velocity, which is v naught cosine theta naught I hat plus v naught sine theta naught j hat, and minus our free fall acceleration due to gravity expression, which has only a y component equal to minus j hat. And let's not forget the time there. So it's actually minus gt j hat. So our velocity has two components. It has an x component given as v naught cosine theta naught I hat, and a y component given as v naught sine theta naught minus gt j hat. This expression for velocity as a function of time will enable us to find the position of our object as a function of time.